Hello and welcome to today's webinar about the pulseEKKO Ultra Receiver. I am Greg Johnston. I am a Senior Application Specialist with Sensors and Software, and I've been with the company for 27 years. I'm sure that most of my audience is familiar with ground penetrating radar, but just in case, a 3-slide introduction. GPR systems consist of a transmitter and receiver, shown here as TX and RX. GPR images the subsurface by firing the transmitter, which sends a pulse of radio frequency energy into the material. When it encounters a contrast of materials, in this case a cavity, some of the energy reflects back to the surface where it is collected by the receiver. Here's an animation that shows the same idea. In this example, the green horizontal line is the surface, and the pink dots are the positions of the GPR's transmitter and receiver, relatively close together. In the subsurface, there is an undulating horizontal boundary where the material properties change. As the GPR energy encounters this boundary, some of the energy reflects and some transmits through. It's important to remember that only the energy that reflects back to the pink dot on the surface is actually recorded by the receiver. GPR has many applications. The history of GPR started with ice and glaciers and ice sheets. And over the decades, as the technology was improved and new antenna frequencies introduced, it has gradually spread into other application areas such as utility locating, concrete scanning, forensics, and archaeology. Today, I want to talk about the deep applications for GPR, mostly dominated by geological and geotechnical applications where a depth of penetration of 10+ meters is desired. Here is an image that shows what I'm talking about. This image was collected with 100 megahertz antennas, low frequency antennas in the GPR world. Notice that the depth of penetration is about 50 meters. The objective of this survey was to image the geological stratigraphy of the area to look for structures that indicate the depositional history. Geologists, geomorphologists, and physical geographers, people a lot smarter than me, can look at the patterns of the GPR reflections and perhaps additional information from boreholes and interpret what these reflections mean. Here are the interpretations the researcher made from the data. To me, the most exciting part of this data is the depth of penetration. Many of you will know that the limiting factor of GPR and the main factor that prevents GPR from becoming a more common and more widely used technology is the depth of penetration. 50+ meters of penetration is not typical for GPR. In fact, most places, 5 meters of penetration is not typical. What today's webinar is about is exploring the quest for deeper GPR data. On the way, I will introduce you to our new Ultra receiver that allows you to see up to twice as deep compared to before. Let's start with the basics. Here's a GPR line. This line is about 75 meters long, and the full depth scale is 75 meters deep, so it's almost a 1-to-1 ratio. But as you'll see, there's not 75 meters of GPR signal penetration. So let's talk about the signals that we see. Now, I'm not sure what other GPR manufacturers do, but sensors and software systems always turn the GPR receiver on a few nanoseconds before the transmitter fires. This allows us to record the background radio frequency noise in the area. We call this RF noise for short. It consists of other sources of radio frequency emissions, radio stations, TV stations, cell phones, military communications, police, airport communications. The sun emits radio waves. The universe emits radio waves. All of these things are potential sources for the RF noise we see at the top of the GPR line. I am coloring the RF noise yellow. Then the GPR transmitter fires, and the first GPR energy, the strongest energy, is the direct air and ground arrivals at the receiver. At this point, the much weaker background RF noise is completely masked by the strong GPR signals. Now the receiver starts to record GPR reflections coming back from the subsurface. These signals get weaker and weaker as they are attenuated by the subsurface materials. The GPR signals are colored blue. Finally, the GPR signals reach a point where they are so weak they have the same amplitude as the RF noise, and we cannot differentiate them from the noise anymore. This point is the maximum depth of penetration. Then the GPR receiver records the RF noise until the end of the GPR recording window. Keep in mind that if your depth setting is not long enough, you may not even see the background RF noise after the GPR signals fade away. Now, I would like to look at this data again, but this time showing the amplitudes of the GPR signals. When the GPR transmitter fires, we get a peak of energy. This is the direct air and ground waves arriving at the receiver. After the peak, the reflected energy with lower amplitudes is recorded by the receiver. The GPR signals are gradually attenuated until they reach zero amplitude at some depth. If we plot the depth of GPR penetration we talked about in the last slide, we see that it runs through the GPR line about here. But notice there is actually lots of GPR signal below the depth of penetration. Why is this the depth of penetration if GPR signals are still present? There is one type of signal I have not plotted, the background RF noise. When we plot the RF noise floor, we see that, as we discussed on the last slide, the depth of penetration is the point where the GPR signal has attenuated to the same amplitude as the RF noise floor. If you look at this plot and think about it for a minute, the depth of GPR signal penetration will increase if the random background RF noise floor is reduced. How can the RF noise floor be reduced? If the RF noise is random, stacking the GPR data will reduce the RF noise floor and therefore increase the depth of penetration. Now, before I actually explain what stacking is, let's briefly talk about how GPR lines are actually collected and what they consist of. GPR lines consist of dozens, hundreds, or thousands of vertical strips of data called traces. A trace is collected at each data recording point along the survey line. This means that each trace has a unique position along the line. The concept of traces was easier to understand in the old days when everyone plotted their data in what we called wiggle traces. In this depiction, the signal reflection amplitudes are indicated by wiggly lines. The bigger the wiggle, the larger the signal amplitude. Now, let me explain what stacking a trace is. If you do not stack your data, or you only stack once, it means that every time you fire the GPR transmitter and collect a trace, you save that trace. Stacking means that when each trace is collected, you fire the transmitter more than once and save the average. For example, if you stack twice, it means you fire the transmitter once, collect the trace, then you fire the transmitter a second time, collect the second trace, then you average those traces together and save the average trace. If you stack 4 times, it means you fire the transmitter 4 times, collect 4 traces, average those traces together, and save the average trace. It's the same deal for stacking 8 times. In this animation, the background RF noise is shown in red. Notice that as you stack the trace more times, the amplitude of the RF noise decreases. There's a mathematical relationship that some of you will know about how the amplitude of random noise decreases with stacking. As you stack, the noise decreases to 1 over the square root of the number of stacks. For example, if you stack 4 times, you get 1 over root 4, which is 2. So the noise decreases to half, or 50% of what it is with no stacking. If we stack the trace 100 times, the noise is 10 times smaller, 1 order of magnitude. If we stack the trace 10,000 times, the noise is 100 times smaller, 2 orders of magnitude. If we stack the trace 65,536 times, the noise is more than 200 times smaller. With the concept of stacking GPR traces to reduce RF noise in mind, I would like to introduce the pulseEKKO Ultra receiver. It's also known as the 3200 receiver. The original pulseEKKO receiver, the 1600, allows trace stacking up to 2,048 times. Well, the new Ultra receiver is much faster and can stack up to 65,536 times. The 1600 receiver uses DEETs, or digital equivalent time sampling, to capture the waveform. The Ultra receiver collects data faster because it uses a faster A to D converter and performs a full waveform capture. Based on our earlier discussion on stacking, let's see the effect of high stacks on some real GPR data. While we were developing the Ultra receiver, we took it to one of our standard test sites, an old limestone quarry near Sensors and Software in Ontario, Canada. In fact, this is the data we were looking at earlier. Here you can see how the depth of penetration has doubled, going from 32 stacks on the left to 32,768 stacks on the right. But let's dive into the results a bit more and understand how the Ultra receiver allows you to see deeper. This is the same sort of signal amplitude plot we've been looking at earlier, but more quantitative and for 6 different levels of stacks. It shows the RF noise floor before the GPR transmitter fires, the peak response from the strong direct arrivals, then the gradual decay of the reflected GPR signals as they are attenuated in the subsurface. Finally, the GPR signals decay back to the RF noise floor, which you will notice matches the noise floor from before the transmitter fired. This plot shows the data at stacks varying from 32 to 32,768. The important thing to note is that the RF noise floor at 32,768 stacks is 45 times smaller than at 32 stacks. If we remember that the depth of penetration is the depth where the GPR signals have attenuated back to the RF noise floor, let's look at how the depth of penetration increases by increasing the number of stacks. The penetration at 32 stacks is about 21 meters, or 425 nanoseconds. The penetration at 32,768 stacks is about 45 meters, or 900 nanoseconds, more than double. Now, I'm sure you're asking, what is this increased penetration going to cost me? As I mentioned, the Ultra receiver collects GPR data faster than the 1600 receiver. In the time it takes to stack 64 times with the 1600 receiver, the Ultra receiver can stack 8,192 times. In the time it takes to stack 512 times with the 1600 receiver, the Ultra receiver can stack 65,536 times. So the increase in penetration depth by stacking comes at little or no cost in terms of data acquisition speed. This is a win-win situation. Let's look at some examples of data collected with a high number of stacks with the ultra receiver compared to a lower number of stacks. In this example, data were collected in Petawawa, Ontario. This area has lots of glacial sand deposits, so it's a good place for deep penetration with GPR. In fact, much of the work in the 1980s developing Sensors and Software's first commercial GPR product, the pulseEKKO 4, was done in this area. As shown here, the 100 megahertz data was collected in bistatic mode, stepping GPR antennas across the ground. On the left is a GPR line collected at 64 stacks. On the right is the same line collected in the same amount of time at 8,192 stacks. Notice how the RF noise on the left is completely gone on the right. Notice how the GPR reflectors that are difficult to see on the left are clearly visible on the right. Notice how GPR reflectors deep in the section that cannot be seen on the left are detectable on the right. Clearly better, deeper data. Now let's do the same analysis on this data as we did with the earlier data. In going from 64 to 8,192 stacks, the noise floor decreased 10 times. It is 10 times smaller than it was before. The depth of penetration increases from about 280 nanoseconds to about 420 nanoseconds, or 14 to 21 meters, 50% deeper penetration. In this example, data were collected in Florida. As many of you know, Florida is generally a great place for GPR because of the sand content. 100 megahertz data was collected with the pulseEKKO system deployed on a smart cart. So it was simply pushed along the surface, and traces were collected every 25 centimeters using the odometer on the cart. The geological setting for most of Florida is sand and other unconsolidated sediments over a limestone bedrock. The limestone is prone to solutioning, that is, being dissolved by the groundwater, which is why we always hear about sinkholes suddenly opening up in Florida and causing all kinds of damage. As a result of the limestone being dissolved, the limestone surface undulates and varies in depth across Florida. On the left is a GPR line collected at 64 stacks. On the right is the same line collected at 8,192 stacks. Again, each line was collected in the same amount of time. Notice how the RF noise on the left is greatly reduced on the right. What strikes me is the curving reflector visible at about 9 meters depth on the right that there is absolutely no clue of on the left image. This is the type of thing that makes me excited about the ultra receiver. Seeing deeper to things we couldn't see before with no sacrifice in survey time. If we plot the line on the right at full scale, now we can try to interpret the data. After talking to some geophysicists at the University of South Florida, who are more familiar with the geology at this site than I am, this is what we think might be going on. Apparently, the strong shallow reflection is a known clay band within the sands. The deeper reflection in the data is interpreted as being the limestone bedrock, perhaps a localized pinnacle. The researchers have said that they have collected GPR at the site for years, but have never been able to image the limestone bedrock before. Now, I know my audience is smart, and a lot of you are thinking this curving deep reflector is an airwave, a reflection from an above ground object that is often seen in GPR sections. If it was, it would have a velocity of the speed of light when you do a velocity calibration using the hyperbola fitting method. It doesn't. It is a real reflection from the subsurface. I will say that there are airwaves in this data. I think some of these higher frequency sloping events are airwaves. The discussion of clearer, better imaged airwaves in the highly stacked data leads to another concept that is important to clarify so there is no confusion. Stacking GPR traces improves GPR data in terms of signal quality and depth of penetration only if the background RF noise is random. Noise is defined as any signals that we are not interested in seeing in our data, but it is important to understand that stacking will only reduce random noise. Any signals that are coherent are not only not reduced in amplitude, they are actually improved by stacking. Let's start with the unwanted airwave. The airwave signal is coherent signal. A simple definition of coherent is that we see a pattern for the signal from GPR trace to GPR trace laterally. This airwave is visible on multiple traces, so it's a coherent signal. Again, stacking improves coherent signal. It does not reduce it. Let's look at another example of coherent signals that we don't want in our GPR data. Here's some GPR data that is badly affected by external coherent RF noise. How do I know that this is from an external source and not GPR signal? I know this because the signals were present at the top of the image before the GPR transmitter fired. In this case, someone in the area of the GPR survey site is transmitting radio signals at a higher frequency, but similar to the GPR antenna frequency. So the GPR data receiver is sampling it as coherent signal. Will high stacking reduce or eliminate this signal? No. High stacking will actually improve the quality of this signal, something we definitely don't want. There's another type of coherent signal that can show up in our GPR data, one that GPR manufacturers don't like talking about. This is called coherent system noise. As the name suggests, it is noise created by the GPR system. Have you ever seen flat-lying signals in your GPR data like the ones in the examples I'm showing here? The right data image is from a sensors and software system, while the left image is from one of our competitors' systems. What causes these signals? The GPR system. It is caused by poorly placed metal cables or metal housings that get energized when the GPR transmitter fires. The energized metal becomes a second transmission source and produces spurious signals that appear in the GPR data, usually as banding. This is coherent system noise. All GPR systems, including ours, have coherent system noise. But what sets good GPR systems apart from bad GPR systems is the amount of coherent system noise that they produce. Some systems are much worse than others. Coherent system noise, shown here in red, is usually very weak and buried in the GPR signals shown in blue. So if the survey site is favorable for GPR with low electrical conductivity, like sandy sites tend to be, the GPR reflections are much stronger than the coherent system noise, and you don't see it. Even a poorly designed GPR system can collect good data in a good environment. But this all changes when you take the GPR system to a site with high electrical conductivity. Soils and materials with high electrical conductivity quickly attenuates the GPR signal. This allows the coherent system noise to be visible. It's within the power of the GPR manufacturer to engineer coherent system noise out of their products. But in my opinion, many manufacturers do not do a good job of this. The important lesson here is that very flat reflectors in your GPR data are more than likely not real signals from the subsurface. They are coherent system noise. But they can look like boundaries And if you're looking for a boundary, like maybe the water table, which you expect to be flat, they fit the bill very well. I've seen many GPR practitioners interpret coherent system noise as real subsurface reflectors. And as we all know, once you put a colored line on a reflection, everyone believes the interpretation. If you see very flat reflectors in your data, be suspicious. Mother Nature is not like that. Okay, a bit of a tangent about coherent system noise, but getting back to the main topic here, you can stack all you want, but coherent noise will never be reduced to improve the real GPR signals. So to take full advantage of extreme stacking to see deeper, you need a GPR system engineered to have low coherent system noise. In fact, when we were developing the Ultra receiver, we started to see signals much smaller than we ever had before, on the order of nanovolts. But we also saw coherent system noise that we did not know existed because we'd never seen it before. And consequently, we had to extend the Ultra receiver development and clean it up before releasing the product. Here's an example that shows coherent system noise as a series of horizontal bands on the left, and after it was cleaned up on the right. Okay, the last case study is from Java, Indonesia. The GPR data was collected on a volcano about 2 kilometers downslope from the crater. The volcano had last erupted in 2015. The area was quite forested with large trees, so the survey area had not been affected by volcanic eruptions for several decades. You can see here that a pulseEKKO 50 megahertz antenna was used, and the data were collected in step mode. Here is a 125 meter long line. It was collected with the Ultra receiver and stacking 32,768 times. The data image is dominated by 3 large hyperbolic responses, which, in case you are thinking it, are not airwaves. In fact, the material velocity was measured at 0.06 meters per nanosecond, which indicates a very wet soil, which is what you might expect for Indonesia. The clarity of the signal and the high quality data meant that the discussion of data interpretation started in the field and not in post-processing. Are these 3 large hyperbolic features buried volcanic bombs ejected from the volcano in some earlier eruption? Or are they lava tubes? This data has not been ground truth, so it's fun to think about the possibilities. So to finish off, the pulseEKKO Ultra receiver increases GPR penetration by stacking thousands of times to reduce the random RF noise floor to reveal weaker GPR signals. There's no reduction in the speed of data acquisition. In some cases, the depth of penetration is more than doubled when compared to our standard receiver. And this is a great advance for the geological community worldwide that is trying to image as deep as possible with GPR. So I want to thank you guys for attending. Keep an eye out for our next webinar, which we always announce. It'll be on our website. We also send an email out to everybody. We put it on LinkedIn. And so watch out for that. And certainly if you have topics that you would like me to cover in a webinar, please send those in. The email address, again, training@sensoft.ca. So do that and let me know what you think.